Okay, so I think I'm alive. Soham confirmed the mic stuff, so everything is working. Can you guys hear the sound and also see the slides? Okay, cool. Thank you. So we start in a better footing today. So thank you so much for joining us. Let me just pull. Okay, so I'll explain in a minute what I mean with part one. But first, you guys know that the Nobel Prize was, announced last week. So a great congratulations to Sir Roger Penrose. I'm highlighting him because he's a mathematical physicist. So hopefully some of you on the audience, the physics students, you will see mathematical physics as an interesting thing to kind of pursue, because normally theoretical physicists take the glory, but it's really nice to see the Nobel Committee kind of recognizing mathematical physicists. And Roger Penrose is one of the greatest mathematical physicists of this generation, a living one. And yeah, it's really great. And he's also a great author also. So I recommend you checking some of his books. It's really inspiring. And you can see some of in his early works, he worked on semi-groups, rings, and matrices, these things that we went through in the early stages of this course. Not as in depth, but yeah. Before we get started, I just want to go through a few things. So these things we are filling up everything green. Huh? So this is all done. We are here. And some of you are eagle-eye will notice that I've added an extra session here. So today will be the part one of this vector spaces, complex vector spaces 101. The reason for that is when we originally set up this program for the foundation module, I didn't have a kind of a better view that I have right now of the audience. So in my view, if we have one lecture where I hit you with everything, it will be slightly harder. So why not just add an extra session and then start very easy, and then next week we take it from where we left today. So that might be frustrating for some of you who are advanced, but yeah, this is it's just, I feel this is the best way. Another thing is this is essentially the start of the linear algebra part of the foundation module, really. And to make things interesting, there will be more or less two approaches for you. The first one is the live sessions, which will be a little bit more, slightly more abstract and maybe heavily algebraic in nature. And also a little bit more tailored to quantum mechanics and let's say quantum computing, because we are dealing with finite dimensional vector spaces. The reason I did this is to prepare those of you who are, if you are to move on to the next module where we will, deal with the very abstract spaces in functional analysis, where I can't draw like a plane with vectors. It's very hard to just put things into a more like the geometrical concept that you guys are used to. So you need to get familiar. You need to get comfortable dealing with the algebra. In fact, this is very interesting because at the heart of it, on the technical side, it's one of the stumbling blocks for uniting general relativity with quantum mechanics, because quantum mechanics is a very abstract theory in nature, algebraic, highly algebraic. It's not just algebra, it has analysis, it has topology, we call functional analysis. And in fact, it's actually motivated some people to, come up with things like, quantum geometry, these things in order to bridge the two things together. So to sum up, the live sessions will be a little bit more algebraic oriented. for the reasons just expressed. And study materials will, in the early stages, will be very aligned to kind of what some of you might have encountered if you had linear algebra before. So you will see like drawings on the plane with the arrows and this type of stuff. And you will see the textbook, actually, the study material that I will share today will show that. And it's too general. It's not tailored to, because obviously it's a general linear algebra. So, it's applied to everything. So it's not really that kind of tailored as the abstract approach that we'll be taking. But then hopefully, as the time goes in the next coming weeks, we will, everything will be centered a little bit more here into the, so things will become a little bit more abstract. So yeah, just to let you know. And starting today, this will make more sense. From the first lecture, I was saying, this is the approach that we will take, start with abstraction, concrete, and then give some quantum hint, or as I initially called it, quantum contest. So hopefully today you will see a little bit of that today, and going forward, you will come across that even more. Okay, so before I go to the first section, does anyone have any questions? Okay, so George is asking, I figured it out, one has to sign up for each. Yes. The reason for this is because, adding people and not being sure that they will turn up is like, it sucks to all the time, porting emails, So this way, you only register if you are able to attend, not the least because we capped the number of sessions to be like a maximum of 50 people. So that way, if you are not coming, it means we have more flexibility to invite other people to join. So yeah. Yes, 1 column down and 2 to go. So let me jump back to the slides. Can you guys still see these slides, by the way? Okay, good. Okay, so there we go. The first definition, actually not even the definition. Let me go through the summary agenda. So we'll start with just quickly go through the additive groups, the axioms of additive groups, just to refresh you, the fields, and then we'll go through the complex vector space axioms. As I said last time, we will jump straight into complex vector spaces as opposed to dealing with complex vector spaces over an abstract field, because that will just take unnecessary time for us to do. We can just dive straight into complex, what matters to you guys. And then we'll go through some examples. We will define the concept of the linear subspaces, linear combinations, linear spans, and then we will end with the Dirac notation, the bra that will come later. So that's essentially, the session will be short, but hopefully the stuff that we will cover and the time that you have until the next session, you will have enough in your head in order to be able to catch up, because next week we will start start moving a little bit faster. Okay, so okay, just to recap, those of you who attended this and watched the previous YouTube video, these are the axioms for a group, in this case additive group, and we've seen that these are examples of additive group. In our case, we are interested in this and maybe this also. So if you don't feel comfortable with you're still having issues with this notion of additive group and these things, just rewatch again, recap the previous lecture and go through the materials that we shared already. Another thing, last week, we went through the definition of field, and one of the sections, we ask which of these integral domains are fields. Obviously, Z is not a field. I hope you already know that. And Q, R, C, and actually F2. In fact, FP, if P is prime, is a field. So just as a matter of a side note. And for us, C is what we are really interested in, really. So anything we do, just think, when I say field, just visualize C. That's what we are interested in, okay? Before I jump to the first definition, is anyone having issues with the concept of additive groups and field? We are all on the same page. Nobody has any issues with it? Okay, good. Thank you. I'll move on. The first definition, let's see. Okay, so here's the first definition. First of all, I want you, to those of you who are new to these things, when you see a mathematical definition, just take a deep breath, don't panic, and go line by line what the definition is telling you. Normally, mathematical definitions are carefully crafted to give you only what you need to know. So in this case, let's go through line by line. Don't panic. Let's go through it line by line. So the definition says a vector space over C being a field, is a triple. So it's a triple made of V plus and this thing called dot. Okay, we'll know what it means in a minute. And then it goes on to say where V plus is an additive group. So the pair V plus is an additive group. Now, because you already know what an additive group is, you can immediately start thinking, that's very interesting, and start visualizing some of the examples that we went through. So far, those examples tick the box, okay? Because they are additive group, okay? And then it goes on the definition to say, the dot is called scalar multiplication in V, and it satisfies these 5 conditions, okay? Let's go one by one. So condition 1, or axiom 1, it says alpha dot psi belongs to V for all psi in V and alpha in C. So it's telling us this scalar multiplication is closed in V. So if you take any alpha in the field C, any psi in V, you do the scalar multiplication, the result is an element of V, okay? And then it goes on, axiom 2. Alpha dot psi 1 plus psi 2 is the same as taking alpha 1 dot psi 1 plus, alpha 1, I'm getting ahead of myself. Alpha dot psi 1 plus alpha dot psi 2 is the same as this, okay, for all, and it's same for all. This is crucial, huh? Okay, for all alpha in the field and for all 2 elements in V, okay? It goes on to say the same thing, so I won't read it because you can yourself read it, so I don't have to, I don't risk, mispronouncing something. So this other condition is also satisfied for all alpha beta in C and psi in V, okay? And it goes on, axiom 4. This is essentially associativity in respect to the scalars. So we call the elements of the field, we call them scalars, okay? So this is also satisfied. You can immediately start thinking, from those examples of the groups that we found we were just recapping before, which ones could be a good candidates to be a vector space over C. And then the final one is that 1 times psi equals psi, right? This is like a little bit intuitive, right? And where where 1 is the multiplicative identity in C, okay? One convention that we will do going forward from today is, we don't need to write all this triple. In fact, in most textbooks, you won't see this. You will just see, the mathematician or, whoever tells you, they will just say V is a vector space, So whenever that happens, just imagine the triple, but we don't write that. And also, we don't write alpha dot psi. You just write alpha psi, because it's understood in the context that this is we call it a multiplication, scalar multiplication. So this is just we'll just take the convention to write it this way. Okay. Let me check the chat, because this is very important. If I lose you here, I will lose you in the next coming lectures. I will lose you forever. Okay. Is anyone first of all, let me ask before we go through the examples, what can be a vector space over C? What's a good candidate looking at the axioms? Let me actually go back to the additive groups, because it says the axioms here say V is an additive group. Let's see. So these additive groups here. Is Q a vector space over C? Yes, C itself, that's correct. Okay. What about Q? Is Q a vector space over C? What about R? Is Q and R vector spaces over C? Think about it. If this is a vector space, or if the scalar, if this can act as a vector space with the scalar being in C. Okay, so let's look where it might fail. Let's look at one axiom. So if you say Q and R are vector spaces over C, that means if you have any complex number, not of course a real number is contained. This R is a subset. Is true. R is a subset of C, but for it to be a vector space over C, it means that any complex number, say take I for example. I is a complex number. If you multiply it with a real number, then the result is another real number. Is that a case? Is that the case? I mean. Yes, exactly. So nothing except C. So C is the only vector from this list of additive groups. C is the only one. Okay. C is the only vector space. Okay. Interestingly, if we are considering the field to be R instead of C, then actually C could be a vector space over R. Okay, because if you multiply a real number with a complex number, you still have a complex number, right? So, but let's not go there. Okay, so it's true. C is the only thing. Okay. Okay, so we are on the same page. Thank you, by the way. I forgot to thank Soham. He's joined me again, and he's very active on the chat. Thank you so much again. Okay, so before we go to a concrete example, is a proposition. Okay, so this proposition, this is a homework for you. Okay. And I think you can prove this. Just go through the axioms again, and you will be able to prove this. Okay. So the proposition says if V is a vector space over C, then the following is true. Okay. So as homework, I encourage you to try to just go through. Mathematics is like it's like imagine you are like a good prosecutor, right? You have like evidence and these things, and then you have to use that to prove something. Whether maybe someone is. Let's say you are a lawyer instead of prosecutor. Okay, you have to prove someone is innocent, so you have evidence you want to prove. So in the same thing, in similar fashion, maybe it's a little. I'm being a little bit sloppy in mathematics. If the axioms are there to help you prove stuff. So I claim the axioms of vector space. If you go back to the axioms, you will be able to prove all this. Okay. Before I move on. I'll just make a notation here. This is just in case some of you are confused. So I was very careful to kind of, because there are, to label this 0V. So this means the zero in the vector space. So let's call it zero vector. That's what Z And this one here, this is the zero in the field. So this is the zero, the normal zero, if you will, okay? So because otherwise, you will be all over the place. Zero, it's like it might give you the impression that you zoom this to it will be like the zero in C, but this is not the case. But in most books, they won't do this, so they will let it, they will kind of leave it to you to guess that this V is the V in the vector space, not the V in the field. Okay, so yeah, let me check the chat. Okay, so here's an interesting prototype example of a complex of a vector space over C. We have already seen this in the group, in the additive, in the group theory intro, where we built C2 like this, So it's like this the column matrix. It takes the entries in C, X, and Y, right? And then we define the addition like this. So you add the individual entries. So that you already know, and you already know that C2 is an additive group. Is an additive group. The only thing now we can do is to define the scalar multiplication like this. So alpha times psi is the same, is just multiplying the scalar alpha with individual entries of the column matrix. And I leave it to you guys at home to scratch your heads. This is very easy, that with this definition, C2 is a vector space over C. Okay? Does anyone have any doubts that C2 is not a vector space over C? Okay. I'm seeing some interesting chat stuff, but I won't get involved. Maybe at the end, I can make some comments if you come back to it. Just not detract from the main session. Okay. So can everyone see? Is there anyone who has any doubts that C2 is a vector space? Okay. So I assume nobody has any doubts. That's cool. We are all on the same. So we are all on the same page. Oh, by the way, this is I saw a comment there about arrows and these things. In physicists normally in their notations, they will put an arrow here to point, like to give a sense of direction in this thing. We're not doing that in maths. There's no arrows. There's nothing. Vector space is a vector space. So that's why I'm saying that the live lectures will be a little bit more abstract. So. Okay, and these are some of the interesting vectors that some of you, especially the guys coming from physics and quantum computation, are familiar with. And we'll go a little bit more into these, actually, especially these two in the coming slides. So these are some examples of very interesting vectors. Over the coming lectures, you will know why. But for today, I'm just highlighting them, okay? Another example. So we can generalize. Obviously, C2, we saw C2 is a vector space. Why not Cn? Okay, so that's true. So for Cn, where n is greater or equals to 1, we can also define this Cn as the set of n by 1 matrices that takes entries x1 blah 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 to xn. Okay, and this is again following the same logic as C2. It's not hard to see that Cn is also a vector space over C, right? And then I added this comment here, and this might not make sense at the moment, but once we come into tensor products, and then before that, even when you learn about vector spaces being of the same dimension being isomorphic to Cn, this will be you will see what I mean with this. So in quantum computation, what you want is to n to be 2, this n to be 2 to the k, where k is greater or equals to 1, and is the number of qubits under consideration. Okay. Do the quantum computing guys, are you on the same page? Do you agree? And there is no doubt that Cn, is a vector space, right? Perfect. So we are all on the same page. I like that. This is the best Friday is when you have everyone on the same page. Okay. So let me move on. Linear subspaces. This is very important, especially in the general abstract formalism of quantum mechanics, because very often you don't deal with the entire Hilbert space. You will deal only with the with the subspaces of the Hilbert space. Okay. So it's very important for you to know what's a subspace. Later in the functional analysis, we'll go deeper, a little bit more abstract into subspaces. But this is like it's still the concept is the same. It's the same thing. So if V is a vector space over C, a subset is linear subspace, or sometimes just subspace. So from now on, if you hear me just say subspace, I mean linear subspace. Okay. Is a subspace if L is also a subspace over C under the same scalar multiplication. Okay. In other words, all the axioms of all the vector space axioms also apply to L. So that makes L satisfies all the vector space axioms. Okay. And here's a prototype. Let's say V equals C2 is a prototype of a linear subspace of C2. Can you all see that L is a linear subspace of C2? Is there anyone with doubts? Okay, so we are all on the same page again, I assume. Indeed, it is. What about this one? If we invert, so we now put the first entry 0, and the second entry can be anything, including 0, obviously. So this is also a linear subspace. Now the question is, obviously, as you can see, the axioms for vector space are very, 5 of them, I believe. So if you are handed a subset of V, is there a way that you can check if that subset is a linear subspace without having to go through all the axioms? Or in other words, as we say in mathematics, is there a minimum and necessary condition for a subset of V to be a linear subspace? Before I answer this, do you think there is? Is that what a span is? Well, we haven't reached span yet, but yeah, we will. Let's say you will be able to answer this once we get to span. Okay, we will cover that also. Okay. Yes, indeed, there is a minimum necessary condition if you are handed a subset of V without having to go through all the axioms of vector space to verify that it's also the subset is a linear subspace. And it's this proposition, it's also a homework, okay? So the proposition says if L is a subset of V, then it is a linear subspace if, only if, these conditions hold. So psi1 plus psi2 is also an element of L. In other words, the addition is closed in L. Condition 2 says the scalar multiplication is closed in L. So if I give you a subset of, if you are giving a subset, the only thing that you need to check to verify that that subset is a linear subspace is to verify that the addition, the addition inherited from V. So it has to be the same addition of the bigger space, which is V, is closed in L, and same with scalar multiplication. Okay, I believe you can do this. If you are struggling with this, you can on the Gitter chat you can ping me later, or maybe actually it would be nice for someone else to help you before I step in, just as a way of solidifying your argumentation. Okay, but this is very easy to prove. You can prove this. I believe you can prove this. And to follow up another proposition as a homework, that's one of the reasons why today's lecture is a little bit shorter, because I have plenty of homework for you. So it says if L and W are linear subspaces, so is their intersection. So their intersection is also a subspace of V. And you can actually use this other proposition to prove this. So all you have to prove in essence is that if psi1 and psi2 belong to the intersection of the two subspaces, then their sum, their addition also has to belong to their intersection. Same argumentation with the scalar multiplication. Okay, so I believe you can also do this. I trust you. Let me check the chat. Okay. Okay. So this is homework. You have a lot to scratch your heads. Now we reach to the concept of linear combinations. Okay. So if you have a sequence, or let's say a list, of or subset, I decided to do it through this list. In the next week, we'll start using subsets. So if you have psi1, psi2, blah blah blah, psi n, their linear combination is defined as a sum. This sum. So in other words, is just alpha 1 times psi1 plus alpha 2 times psi 2, blah blah blah, to alpha n times psi n. Okay, where obviously alpha 1, alpha 2, and so on are elements of are scalars of the field. Okay, so given that definition, you can easily see that if we consider these two vectors, by the way, we can call these elements, this size now, we can call them vectors because we have the vector space and structure now. So if we have psi1 and psi2, and then make alpha 1 and alpha 2, these other scalars, we can obviously create this linear combination. This is probably a little bit familiar with those of you coming from physics and quantum computations. You will see this, okay? And generally, this sequence you will see, the n will be essentially the dimension of the vector space, okay? But we are not there yet. You will come to that conclusion. And another thing that you will see is that all this thing about superposition and this thing, mathematically, that's just a special type of linear combination. In this case, a linear combination that involves orthonormal basis, okay? We don't know yet what the basis is, let alone orthonormal, but you will come to that later. In fact, these two actually, they happen to be orthonormal basis. So therefore, you can actually call this linear combination as a superposition, okay? Okay, let me check. Okay, do we have any doubts? We are all on the same page about linear combinations. This is like easy stuff, I guess, for you, for all of you guys. It's like kindergarten, right? And there's no questions. Okay, I can move on. The next stuff is, this is called span. So this is what Amir, now we are coming to what I believe you were commenting. Maybe not fully until next week, but nevertheless, this is a starting point for what you were just saying on the chat. So if we have a sequence of vectors, psi1, psi2, blah, 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 psi n, we define their span as this set. So it's a set of all possible linear combinations of their linear combinations, right? So for a vector, for a psi to be an element of this span, that means that there exists some scalars, alpha i's in C, such that we can write psi as a linear combination of these vectors in the span, okay? And this is also interesting, well, very easy to answer yes or not, but nevertheless, I will leave it for you to scratch your head. Is psi 1 and psi 2, psi n also elements of the span? Okay? It should be obvious, the answer, okay? Okay, and another question, this is more interesting. Does anyone have any doubts that this vector here is an element of the span of these two? The answer is yes, because we have seen this is a linear combination of this. Okay, and then this brings to another interesting question, maybe a little bit closer to what Amir was saying on the chat, is that if the span is a subspace of V. Who thinks a span is a subspace of V? Yes or no? Is a span a subspace? Yes, it is. It is indeed. Okay? It is a subspace. And for that, we have this proposition, which will also go as a homework for you, which I think you will be able to prove. So the proposition says that the span of psi 1, psi 2 to psi n is a linear subspace of V. So again, this is just a tip. To prove this, obviously, you know that the minimum necessary condition for a subset to be a subspace is, are these two conditions. Addition is closed, so that means addition has to be closed in the span of these two vectors. And the same with the scalar product or scalar multiplication. I didn't realize I'm using the thing. Yeah. So when you say scalar, view this as a scalar multiplication. Okay. Is closed also under in the span of these vectors. Okay. So all you have to do is to prove this. Again, I trust you will be able to prove this. If you are having any difficulties, you can join the Gitter and ping. But I really also on the study materials you will probably see the proof of this. But I recommend you not checking the proofs, trying to you yourself based on the not just on the axioms but also on the previous propositions. This is the kind of the nature of mathematics is like you use stuff, other propositions, other axioms to prove new things, okay? And you need to feel comfortable with this, especially if you are to go on and do research on something, to try to maybe come up with something new, prove something. So you need to feel comfortable doing some proofs, okay? Okay. So this is it. This brings us to the Dirac notation. This is very important, so I'll really ask you to kind of pay attention, because next week we will use it. It will show up all over the place, and if you cannot, you haven't wrapped your head around it, next week you will probably struggle a little bit. So, but it's very easy. Well, it's first of all, this is not a mathematician's creation. This is a physicist thing. Okay. So, but because we are interested, most of you are interested in quantum mechanics and quantum computation, they are all over. The Dirac notations are all over the place, okay? And today we are just touching the ket, because the bra, we cannot yet naturally define bra. One of the approaches that I will take is to define things naturally, we don't have the necessary concept in order for me to define the bra in a clean mathematical fashion. Okay, for that we need two things essentially. We need the concept of dual space, and we need the concept of inner product in order for me to, in a much cleaner mathematical fashion, to define bra. Now, in some of the textbooks, they will tell, especially in finite dimensional cases, they will say, oh, the bra is, okay, the cat is the vector, the column vector, and then you take the row vector, you conjugate the entries, that's bra, okay? Well, how do you define bra in a infinite dimensional Hilbert space, It's like, so I prefer to do it in a clean fashion. And once we go through the dual space and, and the concept in the inner product. In fact, once we get to Hilbert space, the bra will become a little bit more, cleaner to define. That's why we're not going to deal with bra until we get to Hilbert spaces. So for now, it's just the cat. So the cat is essentially just, we were in our notation, we are just using psi to denote a vector. Now with the cat, we just place the psi inside these brackets. This is called the Dirac cat. So in that case, a linear combination, for example, becomes like this. You put the psi inside, and you put the other, its components in there. The psi i's. So another thing in quantum computation that some of you already know, the guys coming from quantum computation, is this vector here. This is denoted as 0. This is the analogous for the 0 bit. This is the analogous for the 1 bit. So that's why they write this like 0, and they write this one as 1. Now, this is not to be mistaken. This is where the confusion can come in. This is not the 0 vector. That's why I wrote here. Do not mistake this thing with with this. Okay. So let me check the chat. Does anyone confused with the Dirac cat notation, or is it like is it clear? Okay. The most it's like it's, I personally don't really, I think it's like an excess of abuse of notation, if you will. But nevertheless, physicists use this, they like using this, and but yeah, and if you want to go to industry, quantum computation and these things, you have to know how to you need to deal with these things. Okay. So to recap, this object here, this is not a 0 vector, huh? This is this. Okay. And then later we will see that for each cat, for each psi cat, we can construct the bra, which is you will see it will be denoted like this. So let me go back to the chat. Yeah, that's a very good question, George. We will come to that again, as I said, when we deal with the dual space. So, okay, I'm going to give you a throw if you want. So, essentially, in general, all bra is an element of the dual space. Okay, so if you know what a dual space, the dual space of a Hilbert space, that's what bra is. But then there is a theorem called the Rees representation theorem that makes the connection between, enables us to make the connection between, the cat and this. I don't want to get into that because we don't have the vocabulary for me to be able to tell you this. Okay, but we'll get there. Okay, so I believe this is understood. It's really important. So go through around and try to play around with the Dirac, with the cat notation. Try to do some linear combinations with it, and you probably you can pick up a quantum computation book or test book or something. You will see all this. Yeah. Let me check the chat again. Okay. So the study material will be this one. I like the title, that's why I picked it. It's called Linear Algebra Done Right. So hopefully the approach that we are taking on the live lecture is not the other way around, linear algebra done wrong, okay? So it's by Professor Sheldon Axler, and it's free. That's why, therefore, I selected it. There were other options, but I think this one is a little bit more interesting. So you will have this available to you later. And just one comment I want to make about the notation. So this highlights what I was saying in the beginning. The live lectures will have a little bit, in the early days, will have different, the approach will be different, and it will also happen in the notation side of things, okay? So in this book, just be aware that he doesn't use the column, I'm using, in this thing, I'm using the column, the column Cn as a column vector. Here he's using vectors in the sense of the Cartesian product, okay? So, but this is not a problem because, the two things, you can just view the two things are isomorphic, right? They are the same thing. It's just a choice of notation, So if you come across something like this, just imagine, invert it, make it into a column matrix, okay? That's and then you will come to the same conclusions that he gets into in the study material, okay? So yeah, just be aware of that. The notation is slightly different because he's using the Cartesian notation to denote the components, the vectors, as opposed to using the column matrix approach that I'm using on the live sessions, okay? Okay. If you have another test that, that's why I recommend join the channel. Please feel free to share it, Ryan, on the Gitter channel. By no means I'm saying like, just stick with this. If some of you have another reference that you can, you think it's good enough, interesting, just feel free to share it. So yeah, share it on the chat, and we can add it on. And send actually you can, if it's free and there's no conflict of like copyright and these things, if it's freely available, you can send it to commit it to the GitHub repo, and I will accept it, or give it to Amir. Amir is one of the contributors. Amir will do that for you. So yeah. Okay, so Ryan is suggesting some other books. Please, for those of you who have any suggestions of other books, feel free to post on the chat or submit on the GitHub. This will help all of you. Okay, so another thing I want to say is the final thing. As I said, today's lecture is like a walk in the park. It's very easy. This is just to prepare your mind for next week. Well, we'll go through much more things, a little bit more, and we'll up the pace. So again, the slide materials and the book, the free book, will be available on the GitHub repo. If you want to rewatch this session again, just to go through some of the stuff, go to YouTube. You can also follow us on Twitter. And most importantly, I really encourage you to join the Gitter, because if you have any questions, just interact. Go there and post the questions there. If nobody else can address the question, I will come in and try to address it. But I really encourage each of you to kind of try to interact, try to answer. Like Soham, actually, many thanks to Soham for being active on the thing on the Gitter, by helping. So this is really good. This is what we want, is to build this community where you can help each other out. It's also a way of testing, the stuff that you learn, whether you learn it here or learn it elsewhere. So it's I really encourage you to join the Gitter. With that, I forgot actually to add this, but some of you already have read the announcement. So on the 20th, we have our first fireside chat with Amira Abbas. So I've already sent invitation. If you haven't received the invitation to register yourself, please just reply to the messages or go to the chat and let me know. I'll send you the invitations. So it will be like 2 hours before the normal times. So yeah, it's really interesting because Amira comes from a very interesting background that I hope will inspire you to pursue quantum computation. So yeah, with that, this is it really. I'm now open to questions if anybody has any questions, whether related to the lecture or something else. Or was there anything in the chat before that people were confused about that maybe I could help? I'm sure that Soham and the rest have addressed the questions, but yeah.
I think pretty much all the questions were answered today. I don't see any lingering questions out there.
Okay, good. In that case, thank you so much, everyone. And yeah, this is it now. In the last few lectures when we started, I hope this journey has been very helpful for you to be able to understand, have this understanding. And from now on, it's like, you will become even more exposed to more things, more relevant things to quantum mechanics and quantum computations, even though we are in finite dimensional stuff. But yeah, nevertheless, I hope you enjoyed it. And yeah, I see you next time. Thank you so much again, Soham, for your help, not just in chat, in answering the questions in the live session, but also on the Jitter community channel, but also for helping me with the sound checking and these things. So thank you so much. Okay. Okay, so I'll see you next week then, and have a good weekend.